with that, we have seen sufficient number of implementations of decoders and multiplexers. One other natural thing that you can do now, right, is just like we asked in the decoder case, right? Can I implement a 2:8? No, let's say 2 power 4 is to 1 mux, okay, using 8 is to 1 multiplexers, right? Or let me say 2 is to 1, 2 is to 1 multiplexers, okay? This is what I essentially want to do, just like in the case of the decoder, right? So what do I have? I want the following, okay? I want the following: y mux, okay? So this is I0, I1, I2, I15, okay? And I have how many select lines? I have 4 select lines: S0, S1, S2, S3, okay? I have 4, okay, S0, S1, S2 and S3, right? Now I want to implement this huge multiplexer using just 2 is to 1 multiplexer. So what is the 2 is to 1 multiplexer? It's a much smaller thing. I have only 2 inputs, I0, I1, and my output um, output Y, okay? And I have just one select line, which is S. Okay, if S is 0, I0 will go through. If S is 1, so the multiplexer 2 is to 1 mux is like this. Okay, S, I0, I1, Y, 0, 0, 0. You can write for all 8 combinations actually. 1 0 0 1 0 1 1 1 0 1 1 1, okay? If S is 0, it is going to simply choose I0, okay? And when S is 1, it is simply going to choose I1, okay? This is what it is. So 0 1, right? So this is going to be 0 0 1 1 and 0 0 1, no, sorry, 0 1 0 1, right? And if you do the Boolean simplification, you will see that Y is equal to S bar into I0 plus S into I1, right? So this is what we have. Now the question is, how do we implement the multiplexer, which is a 16 is to 1 multiplexer, using these 2 is to 1 multiplexers, okay? So just like the case of the decoder, remember, we have to now start from the input because we have 16 inputs, right? And you need how many multiplexers to first of all accept 16 inputs, right? So it's very clear, you have 16 and each of the the component that is given to us, this component can accept 2 inputs. Therefore, you need 16 by 2, 8 such multiplexers at the input stage first of all. Okay, so I will just draw that. This is in groups of 2, I0, I1, right? I2, I3, you go all the way down. I14 and I15, okay? Now this, each 2:1 multiplexer is going to give you one output, right? And that needs to, remember, finally we have to select only one of these 16 cases, okay? So what should the select line of these 2:1 multiplexers be? I think that's the first question that we need to answer, okay? So let me just move this a little bit up so that I get some space. Yeah, this is good enough, okay? So I have this. So the select line is obviously, S0 is the LSB, okay? So let's see what happens if I connect this to S0. All these select lines are going to get connected to S0, right? Now, next, therefore when S0 is 1, S0 is 0, you are going to select either I0, I2, I4, I6, even inputs, or when S0 is 1, you will select the odd inputs, I1, I2, I3, I5, I7 and so on, right? This is how it's going to go. And next, what I need is, I have 8 inputs, right, that are going to the next stage, and therefore what I need from there is actually another 8:1 multiplexer. Now how do I implement an 8:1 multiplexer? I need 8 by 2, that is 4 2:1 multiplexers in the next stage. So therefore, I will just okay. So I will call these outputs, let me give it a name, x0, x1, x7, okay. So this will come here, right, and x7 will come here, and this will be x6, okay. Now I have to connect this select line. So what I do is, I pick the next select line, S1, like this, right. Now this will select and give me how many outputs. There are 4 multiplexers here, and therefore I will have outputs U0 to U3, okay, and therefore now I need a 4:1 multiplexer, okay. So therefore that again I need 4 by 2, okay. So this is going to be U0, U1, U2, U3, right, and the select line here is going to be S2. Finally, I have 2 outputs that I need to pick from, and that is going to give me the last stage, okay. This is going to be select line S3. So this will give me V0, V1, and finally I'll get YMUX out here. So if the input happens to be 0, 0, I mean the select line happens to be 0, 0, 0, 0, right, then the input I0 will flow through this path, okay. On the other hand, if the input happens, select line happens to be 0, 0, 0, 1, that is S0 alone is 1, then the I1 will flow through the multiplexer in this path, right. And let's say that the select line happened to be S3 was 1, S2 was 1, S1 was 1, but S0 was 0. That means we are going to select input 14, 1, 1, 1, 0. Okay. Then what will happen? Your I14 will flow like this, into this, and then into the MUX, right? So effectively, just like you saw with the decoder, in order to build a hierarchical decoder, we had to start with a decoder on the output stage, then divide by 2, that we needed a decoder for that many outputs in the previous stage, again divide by 2, keep dividing by 2 until you reach the point where you have your smallest decoder or multiplexer that you have can accommodate those number of inputs, right? Exactly the same thing here, right? So now I will define this as my level 0, not I'll yeah, level 0, level 1, level 2 and level 3, right? So you needed 4 levels in order to get this thing, right? Now we can also look at an alternate implementation. Same, I want to do 16:1 MUX, okay, using a 4:1 MUX now, okay, as opposed to a 2:1 MUX. So first of all, in level 0, okay, L0, we are going to now this is L1, and we'll see how many levels we need, okay. So first of all, I need 1, 2, 3, 4, right? I need 16 by 4, right? Because each multiplexer that I have, a 4:1 MUX, can take 4 inputs. So I need 16 by 4. I need 4 such multiplexers, okay. So I'm going to call this M0, okay. Then I have my next multiplexer here, 1, 2, 3, 4, okay, M1, and okay. And the select line, I will just indicate the select line here. Each of them have 2 select lines, okay. And of course, by the way, the multiplexer that we want is actually that is already here, right? We need a 16:1 multiplexer from here, right? So let me copy this. This is what we need, okay. So what am I going to do? I am going to connect the inputs I0, I1, I2, I3. This is I15, I14, I13 and I12, right, and so on, okay. Now the two LSB bits are S1 and S0, okay. So I am going to assume that this is S0, S1. So in level 0, I have 4:1 multiplexers that are giving me this, right. Now the output of the first stage are how many? I have just 4 outputs, right, and therefore the second stage, level 1, is very straightforward. I just make another 4:1 multiplexer here, right, and then put my select bits S3, S2 out here, okay. So okay, so this is S0, S1, S0, S1, S1, right? And therefore, I'll call these outputs as X0, X1, X2 and X3, and this is my multiplexer number M4, okay. So, with just 5 4:1 multiplexers, we were able to implement a 16:1 multiplexer, right. So, now you can make a very similar calculation if you were to implement a 64:1 multiplexer, or if you were to implement a 128:1 multiplexer, right. So, it's very straightforward how many levels you need and stuff like that. So, you can I urge the viewers to please make these theoretical calculations and see for yourself how many such components you would need if you were to go ahead and implement this hierarchically again, right, hierarchically, because we are starting with 2 power n, coming down to 2 power n minus 1, right, 2 power n minus 1, then 2 power n minus 2, you are dividing by 2, you keep dividing by 2 and eventually get the output to 1, right. So, just like we did for the decoder, again, it's not necessary that the inputs must always be, number of inputs should be in powers of 2. You can have non-powers of 2 where you just remove some multiplexers, right, and then figure out how to implement it accordingly, right. So, with that, I will conclude this discussion on the hierarchical implementation um, of components using the building blocks that we already had with us, right. So, just on the topic of a multiplexer, there is also something called a demultiplexer. Right, a demultiplexer is basically you accept one of the inputs, you accept one input, okay, you have an input I, single input, and then you are going to decide which of the 2 power n outputs will get this particular input, right. So, this is y0, y1, y2 all the y2 power n minus 1, right, and I have select lines like this, okay, S2, S1, S0. No, I cannot say S2, S1, S0. I will say S0, S1 all the way to Sn minus 1. So, n select lines 1 is to 2 power n DeMUX, okay. So, again, we can you can think about how this whole thing must be implemented, right. So, it is possible to do this in multiple ways, right. So, what is the basic idea here? The input yk, right, is simply going to be the min term mk divided into and I, right. So, essentially if Sn minus 1, S1 all the way to S1 to S0 are all 0, then min term 0 will go to 1 and you want the output y0 to have the input I, right. So, sometimes it may be painful to write this in terms of a truth table, but we could attempt that also. So, the input I Sn minus 1, Sn minus 2 all the way to S0, outputs are y0, y1, y2 power n minus 1, right. The input is 0, all zeros, then my output will be 0, right. These of course will all be 0, right. If the input is 1, then this of course all this is 0. Maybe I'll put the input here as the least significant bit. If this is 1, then output should be 1. All of this will be 0. If this is 0, 0, all the way 1, and this is 0, 1, right? Then this will be 0, y1 will now follow my input, right? This is how it is going to be, right? And therefore you can just say yk is the kth minterm ANDed with the input I, right? So again, how would you implement this? The implementation is very straightforward. Let's just look at it again from a from a hierarchical implementation. Assume that you have a decoder as usual. This is a decoder which is n is to 2 power n decoder, right? And I have my select lines coming here, S0, S1, Sn minus 1, and I have the outputs y0, I'll not call it y0 because the demultiplexer output is also y0. So let me call this x0, x1, x2 power n minus 1. Okay, the enable to this decoder, I could just tie it to 1 if you wish. Okay, and then what I can do is to simply use x0, right, and okay, and AND it. Okay, I have the input I, which is common to all these AND gates. Okay, and I'm going to AND it. Right, yes, so I get the outputs y0, y1 all the way to y2 power n minus 1, right? So with that, we have been able to implement a demultiplexer as well, right?